So in today's session, we will see two concepts: causal order violation and global state recording, that is GSR. So before we go into the protocols that we will be talking about in this particular area, let us revisit what we talked about causal ordering of message violation in the last session, and where can we apply this concept that we are learning through these protocols. So I'll go to whiteboard and probably I'll share one or two examples of causal order violation. So here if you see, let's say there are two sites, site 1 and site 2, and there is a message which was sent by P1 to P2, and this is of course your time axis, global time, and this is your message 1, M1, and after some time message M2 is being sent by P1 to P2. So if everything is all right, it will come actually a message like this. So if you see the receipt of these two messages, this is your message M2. So message M2 is being received after message M1 is being received at P2, because the sends of these two messages are also causally related. Send of M1 is preceding send of M2. So here in this example, you can say there is no causal order violation. But if I draw another diagram for the same communications, let's say this is P1, this is P2, and now your message M1 is being sent here, it is reaching here, P2, but message M2 which is being sent here is reaching here. So you can say that M2 is being received by P2 earlier than M1, whereas M2 was sent after M1 is being put into the channel by P1. So this example is actually a violation of causal order. So M1 and M2, these are the two messages, when they are being received at P2, are not maintaining the right causality at the receiving side. Whereas here you can say that there is no violation of causal order, everything is all right when it comes to this particular example, whereas here it is not so. So now the question comes here is, where should we use this, or where should we apply this particular concept? In the last session we saw several examples like your checkpointing and recovery. You can use this. You can use this for your group communications. For example, if there is a multicast communication which is going on and there are multiple senders in the multicast communication, and the order in which these multicast senders are sending their messages are defined in a particular order. So let's say send 1 is happening first and then send 3. Sender 3 is sending. But these two sends are being received by those multicast receivers who are all forming a group in a different order. Message 3 is being received first and then message 1. Then you should say that this will violate, or this will do something wrong to our multicast communication, and hence although the message number 3 is coming first, we will not receive it at the receiving side. We will buffer it or we will queue it, and then probably we will receive message 1. Definitely message is going to come. Unless message is being lost, we will definitely get it after some time, and then the one which we have deferred or we have buffered in a storage, we will deliver it. So the meaning of your multicast communication is not changed or is not impacted. You can also apply these causal ordering message protocols that we learn through this for the purpose of replica maintenance. Like if you have a file being kept at 3 different places for the purpose of reliability or availability. So these 3-4 places are holding the replica of this particular file, and you do a lot of updates on this file from time to time, and all those updates, when you send through different sub transactions or transactions originating at multiple nodes, all these transactions should be performed in the order in which they were originating at those sender nodes. So if you do a violation to this order, probably your copy of the file or copy of the replica that is being kept at multiple locations will be different, hence violating the consistency requirements. For example, one copy could give you a value of 5, other copy could give a value of a variable as 6, third one could give you a different value. So to overcome this particular replica inconsistency problem, although we are receiving these updates in different orders, we will ensure at the end the right order is preserved or right order is maintained, and then we carry out all those updates in that order only. So with this much of understanding, let us now go to the protocols that we will see under this. 2 protocols we will see which will help us in seeing a scenario like this, but converting this into a causal order. So how will you convert this into a causal order is, although you receive M2 first and then M1, do not deliver M2 to P2. Simply buffer it. So if I simply now draw a diagram where instead of delivering M2 here, I am saying I will buffer it and I will deliver M2 here at this point in time. So it's a single message. Although I am using 2 different colors, it's a single message. Fine. So the moment I am diverting its path from this particular place to a place which is in the time axis which is greater than the time at which M1 is being received, you can see the causal order is maintained. So basically I am converting a diagram like this to a diagram like the one which is shown in the left. So now let us come to the protocol that we will see. Not one, we will see 2 different protocols using which we can convert any time space diagram with causality violation, that is messages are violating the causal order, into a system where messages will be delivered as per the causality of those send and receives. So the first protocol that we will see today is this Birman-Cifers definition. This is again a research paper or a research article published by these 3 people, and they they have given it, and I am abbreviating it as BSS protocol. I got a question from Mr. Saurabh, how to identify which message is going in buffer. Yeah, so we will come to that. Basically the message which will go to buffer is the message which should not have reached the receiver at that point in time. So how to identify will be decided by the protocol that I am listing in this slide. We will apply this to few examples and there it will be cleared. Fine. So now let us look into the protocol, what it says. These are the steps. Now this BSS protocol is actually a protocol which is suitable for broadcast communications. So when you say broadcast communications, it's a message which is going to all. Whenever there is a send should not leave any node in the whole distributed platform. If you have 30 nodes and one is sending, then it should go to all remaining 29 nodes. So this is how the broadcasting is to be implemented, and that is what one of the prerequisites of this particular protocol, to make your system a broadcast communication first and then apply your BSS protocol on that. So the first step says, before broadcasting message M, process PI, the sender, increments the vector time VTPI, and this vector time is put as a piggybacked message in the message. So this is, in other words, you can say it's a timestamp that we are giving to the message, and that timestamp is nothing but what value the vector time is giving for the event that is being broadcasted. This is the first step. So basically you have to apply again those IR1 and IR2 of vector clocks to realize this particular protocol, and again we will not apply those IR2 as it is the way we read in the previous vector clock algorithm. We will probably apply only the maximizing part of the IR2 implementation rule 2 of the vector clocks. I'll take examples. Then the next step, process Pj, which is not equivalent to Pi, receives the message M with a timestamp denoted as VTM from Pi and delivers this, delays the delivery of this message until both these two conditions are satisfied. So this is important here. The first condition says VTPJI equal to VTM I minus 1. So VTM is nothing but the timestamp and VTPJ is the vector clock of the receiving site. So this particular rule actually is used here to ensure that a process which is receiving this message also has received all previous messages coming from the same process. Similarly, you have one more rule, VTPJK, leaving the index I, that is nothing but the sender's index, the other values of this vector clock, that is all the k's, because k is from 1 to n, leaving I, you can see the right hand side. VTPJK must be greater than or equal to VTMK for every k. So this is again second clause or second rule. Now this rule is used here to ensure that the site which is receiving this message also has received all messages received by Pi before sending message. So this is basically for indirect receipts. So unless these two rules are true, suppose first rule is satisfied but not the second one, still then you cannot deliver the message to the receiver. If second is satisfied and first is not, still then you cannot deliver. So both the rules should be satisfied to allow you to deliver that particular message to a receiver. Now when you are through with these two conditions, simply increment the vector clock of the receiving site for that particular event, which is nothing but a message receive event, by IR2 of the vector clock. Now this IR2 says that we need to take a maximum of the clock that is accompanied in the message and the local clock of the receiving site. So we will do a maximization of these two values, and hence that will be the clock value at the receiving site of the process time space diagram. So with this we will now solve one or two examples, and then if you have any doubts there you can ask me. I will clarify those. And we have one more example here. Before we come to this example, I will go to whiteboard and probably take a simple example first, and then we'll come back to the example that is there in this slide. Fine. So let us now apply BSS to a simple example where I will say that this is, let's say, there are two sites in the distributed platform, site 1, P1, P2, and again let us take the same example. There is a message which is going here. There is another message which is coming from P1, but it is reaching to P2 here. That is before the first message is being delivered. So now in this, how should we apply our BSS algorithm? The first step is, before broadcasting message M, increment its local index, that is apply IR1 of the vector clock. So now there are two sites, so you will have two values in the vector clock, two scalar values. I'll denote them as, let's say now when I'm incrementing the first value, so it will be 1, and the second value will be 0 because nothing has happened to the second index is for P2 actually. So this is now the vector clock value for this event, that is the message send event. And of course it's a broadcast communication, you can see, because there are two. So whenever there is a message which is sent by P1, it should go to P2. Whenever a message is being sent by P2, it should only go to the other one, that is P1. So hence this example, the diagram that I have shown in this whiteboard, is nothing but an example of a broadcast communication. Fine. Now let us see what will happen to this. This is also a broadcast or a message sent. Whenever we do such message send or broadcast, we will apply again IR1, incrementing its own index. So this will be 2, 0. Fine. Now, these clock values are accompanied or piggybacked or sent along with these messages. So this message that is coming will also come with a timestamp 2, 0. This message also will come with a timestamp 1, 0. Now, when you look into the time axis, that is x-axis here, global time, we will see first what to do with this particular point. So now we'll see those two clauses or two conditions. Here you have 2, 0. Now if you see who is sending to whom, it is 1 is sending to 2 or P1 is sending to P2. So look into the ones value. So this is ones, this is twos. There are only two values. So now the value, the integer value for position 1 is 2. And what is the clock value just before this message is arriving? It is 0, 0, because there is no event which has happened at P2 till this particular point in time. So although I am drawing a vertical line just outside the circle, you can even take the point here just before the arrow. So now this is 2. So the first rule says that VTPJI should be equivalent to VTMI minus 1. I is nothing but 1 here. So if you said this, take 2, 2 minus 1 is 1. Now you see the first position of this clock. This is 0. So you have 1, 0, and this is 1. So VTMI minus 1 is this value, and VTPJI is this value. Now these two, are they equal? They are not equal. So as they are not equal, you cannot deliver this message here. We need not go to rule number 2, right? VTPJK must be greater than or equal to VTMK. So we don't need to check that. Although that condition is satisfied in this case, because you can see 0, leaving I, we have to look into other values. So there is only one value 0. This 0 is greater than or equal to this 0. That is true. So the first condition is not met or satisfied. Hence, you cannot deliver this message. So let me number those. Maybe this is M1, this is M2. So M2 cannot be delivered here. So I will write that this is to be buffered or deferred or queued. Any name that you can use. So we are buffering this, and now probably we will say that, okay, so here I'll put a cross. This is a buffered message. Now this should come after this particular received. So now let us do the same thing for the first message that is coming up. So the timestamp that is coming up is 1, 0. So 1 is sending to 2. So 1 minus 1 is this 1 you have to take. 1 minus 1 equal to 0, and the clock value still is 0. That is true because you didn't do with the first value of the clock, 0. So first condition is satisfied. Next you can check the second condition, this 0, VTPJK. Remaining elements of the receiving clock must be greater than or equal to this VTMK, the other values of the message except the sender's index. So both the conditions are true, hence we can deliver this. There is no problem in delivering this message. Now when we deliver this, we apply IR2. So IR2 says that take only maximum of this value and this value. So max of, this is a vector comparison that you have to do, 1, 0 and 0, 0. Max of these two vectors is nothing but 1, 0. So hence the clock value at P2 will be now incremented from 0, 0 to 1, 0. This is not exactly as per the vector clocks because we are not applying again IR1 after applying IR2. We are only applying IR2. We are only doing the maximization of those two clock values. So here our purpose is to see that are we able to get the problem of causal order violation solved or not. All right. Now let us see, can we deliver this or not? Yeah, I got a question from one or two people. Shasikala, can you explain how it is 2 minus 1? Okay. This 2, you are talking about this 2. So if you see the protocol, this is VTMI minus 1, right? So this step I am explaining. Okay. Then Mr. Saurav asks, how is it 1 minus 1 same logic? This one, you have to basically subtract 1 from that. So through that, what are we doing? We are actually checking whether all the messages that are sent before that particular message are being received or not. So if you say it is 1 minus 1, that is 0. So it means before this message, there was no message which was sent by P1 to P2. Whereas when you look into this particular value, if I do this 2 minus 1, that will give me 1, and that 1 is nothing but one message was sent before this particular message is being sent from P1 to P2. That is what we are checking here. Now there is another one which has come from Mr. Kumar. In P1, if there was internal event happened between 1, 0 and 2, 0, then second message towards P2 would have denoted as 3, 0. Then how 2 minus 1 logic works for P2? No, okay, I'll answer Mr. Kumar's question. What I understood from your question is, if you have internal events which are happening, then you will also give those. So if I simply put one more dot here, it will increase the value. But now when you go to the message send, it will not be 2, it will take that value. So if I put a dot in the middle, I'll have a clock value for this event, and that clock value will be used while computing this value, right? So you can take few internal events, few message send and receive events. See, our significance here is to use message send and message received. That's why I have not taken any local events. You can try this example by taking few local events also, but you will get the problem solved correctly. I'll take 1 or 2 more examples also. So there is one. Mr. Pradnesh, not able to understand 2 minus 1, because 2 is the clock value. You have to subtract 1 from that, just to ensure that whether all the messages before, see, how will I say all the messages? If the value is 3, it means there are 2 messages which have already been sent. If the value is 2, then there was another message which was being sent earlier, right? That is what it is saying. So second step is, I will take second step in a different example. Now with this, we will let us now see the actual thing we did not do here. We will see now, can we deliver this message here? Do the same exercise again. So this is nothing but 2, 0 is the clock value that is coming up from this particular message. So now we will do this 2 minus 1, that is 1, and you have already got a 1 here, right? So first condition is satisfied, which was not happening earlier. Then the next element, the 0 is greater than or equal to 0. Hence, you can deliver this. So when you are delivering, you will update it with the maximum. So maximum of 2, 0 and 1, 0 is nothing but 2, 0. Okay. So this is one example I took. Now let us take 1 or 2 more examples, and then we will come back. I will come back to all your questions that you are asking. Fine. So let us take one more example here, and probably if you have understood the previous example, you can solve this problem. And I'll take a more complex one in the whiteboard, maybe after this. So although it looks like there is no causal order violation, but there is a causal order violation in this particular example. You can see, is it a broadcast communication or not? Answer is yes, because there are 3 sides and every message is going to 2 other sides, leaving the sender. Hence, it's a broadcast communication. So P3's message is going to P2 here, P1 here. P2's message is going to P1 here and P3 here, right? So if you now see that there was a message which was sent here, right? And its receipt is here. And after that, there is a message which is going here. Now, receipt of this message is reaching here before this particular message. So here is the problem. So now, if you solve this, you will come to know how should we solve. So there are three values. We will now give three values to this. So probably this is 0, 0, 1. First position I am keeping for P1, second position for P2, third position for P3. So this is my vector clock value. Sometimes you may find 0, 0, 1. This is notational difference only. So you can even remove that comma. So this is my vector clock. Now let me see, can I deliver this here or not? So this message is coming with a timestamp VTM as 001, right? Now I will subtract, so it is 3 sending to 2. So I will subtract 1 from this value, wherever I am underlining. So 1 minus 1 is 0. And check, so now at this point in time, what is the clock value? All 3 zeros. And check the corresponding value of the clock at P2, that is this 0. So 1 minus 1 equal to 0, and we have 0 here. So first condition is met. That out of those two conditions, first condition Vt Pji equal to Vtm I minus 1. Now check Vt Pjk. So this is the two values now. Leaving the third one, you have now 1 and 2. This 0, 0 is greater than or equal to 0, 0. This is true. Hence, now message can be delivered. If this message can be delivered, we will simply update it with IR2. So that says that the clock value is 001, the timestamp is 001, and this is of course 001. Now when I say this can be delivered, you do a maximization of 001 and 000. So this will be 001. Hope I am clear to all of you till this particular point. Now please bear with me. I will explain condition 2 also again in another example. Okay. Mr. Senthil says, won't it be 011? No, it won't be 011. That's how the protocol says. We are not applying. So in the vector clock, yes, it will be, if you apply vector clock as it is, it will be 011. So in this protocol, without incrementing the local index after applying maximizing function, right, we need to assign that timestamp to this. See, our objective here is not to see whether we are getting the vector clock values correctly or not. Our objective here is to see that whether we are able to change a violated order into a non-violet or right causal order diagram, right? Okay, so 001. Now let us see the second, what is the value for these? This is again a broadcast. So we will increase its own index first. So own index means P2. So I'll make the middle value 1 first. So this is the middle value. Then the first value will be 0, and the third value has already become 1. So this clock value will be 011 for this particular broadcast, right? Now 011 will be the timestamp that will go with this message, and 011 will be the timestamp that will also come with this message to P3, right? Whereas this is going with 001. Now you can see whether we want to buffer or not. So if I talk about this particular event, you have this clock 011. So it is 2 is sending to 1. So you simply look into the middle value 1, this wherever I have underlined. So 1 minus 1 equal to 0, right? And what is the clock value just before this? All 3 zeros. So now look into the middle position of P1's clock. It is 0. So now this 0 and this 0 are equal. So your first condition is satisfied. There is no problem with the first condition. Now we will see the next condition. Yeah, I was getting actually a question to explain second condition. I am explaining that, Mr. Siddharth. Yeah. So now the second condition says that you need to look into other values of the receiving clock. So this middle value we have completed. Second condition is true. The first condition is true. Second condition says look into remaining values, this 0 and this 0, right? So you have this 00 at the receiving side, and what is there in the timestamp here? This 0 and this 1, right? So we have this value. Now you check whether this one is greater than or equal to this value. Answer is no, because this 00 is actually less than equal to this 01, so it is not greater than. So it means we are looking for a more up-to-date time of the scalar value in the vector at the receiving side. So this is what the second condition is. It is not true. Hence, you cannot deliver this message. Pooja Malik asks, how is the previous value 000 for P1? Oh, previous value 00 because there is no event which took place. So we are initializing all the clocks to 000, right? If you would have attended last session, probably we talked there. Initially, all the clocks are set to 000 because there was no event which took place in P1 before this particular message that is arriving. Hope I am clear now. So hence we will defer this message. Now as we are deferring this or delaying this, it has to come at some other time. I'll just stop recording and then restart.